Hello, once again, you're welcome to my channel. Today we'll be looking at Module 1 of the CCNA3 Enterprise Network Security and Automation. And Module 1 is on the topic Single Area OSPF version 2 concepts. Now, we need to understand what OSPF is and why we are studying it. In CCNA 1 and part of CCNA 2, we were able to understand the concept of network protocol. And we said that a protocol is a set of rules that describes or that governs communication over a network. And we also introduced in CCNA 2 the concept of routers and how they interconnect and work together on a network. Interestingly, these routers have certain protocols that are configured on them, and these protocols are rules. So one of the protocols that we're looking at is OSPF, Open Shortest Path First. That is OSPF. So in this particular module, we're going to explain how single area OSPF operates in both point-to-point and broadcast multi-networks. Now, interestingly, we are also going to be looking at the fact that we will share some videos and we'll share some videos and you will learn one or two things from that. So when we get to that point, I will let you know. So let's delve into it. OSPF features and characteristics. OSPF is a link state routing protocol that was developed as an alternative for the distance vector routing information protocol. OSPF has significant advantages over routing information protocol in that it offers faster convergence and scales to much larger network implementations. Convergence basically is the state in which a particular router has a full knowledge of the entire network that is directly or indirectly connected to. So when all the networks within a particular device are converged, it means that that particular device or that particular router has a full knowledge of everything that is there. Now, OSPF is a link state routing protocol that uses the concept of areas. The areas now is just like a way of grouping. You are grouping networks into categories or into areas, into whatever areas that you can form, but number the areas, area 0, area 1, area 2. Now, each area has a collection of routers that work within that particular area. So a network administrator can decide to divide the routing domain into distinct areas that can help to control routing traffic. So a link is an interface on a router, a network segment that connects two routers, or a stub network such as an Ethernet local area network that is connected to a single router. You may want to find about what is a stub network. It's basically a network that has one default gateway that routes its packet. Information about the state of a link is known as the link state. Okay, so the state of the link could be maybe it is up, it is down, it is propagating, it is advertising, it is, so the status or the state of that link is what we call the link state. So all link state information includes the network prefix. The prefix now could be either /10, /20, /24, /30, /32, whatever. The prefix length and the cost. So this topic or this module covers the single basic OSPF implementation and configuration. Now, there are certain components that we need to understand when it comes to OSPF. So all routing protocols share similar components. They all use routing protocol messages to exchange routes. information. So the messages help build data structure, which are then processed using a routing algorithm. So routers running OSPF exchange message to convey routing information using 5 types of packets. We have the hello packets, we have the database description packets, we have the link state request packet, we have the link state update packet, we have the link state acknowledgement packet. So these packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about the network. So OSPF messages are used to create and maintain 3 databases. They are what we call the adjacency database. We have the link state database. We have the forwarding database. Now, this adjacency from the word adjacent is centered on the neighbors, the list of all neighboring routers, which a router has established bidirectional communication with. So this table is unique for each router. So that's the neighbor table. So if you use the command show IP OSPF neighbor, if you use this particular command, it brings out this neighbor table. All right. And this is what the neighbor table contains. Then if you use the command show IP OSPF database, show IP OSPF database, it lists the information about all other routers in the network. So the database represents the network link state database. Okay, and all routers within an area have an identical link state database. So this particular command, show IP OSPF database, displays this topology table. Now, the routing table on the other side actually is discovered using show IP route. If you use show IP route, it brings out the routing table for you. And it contains a list of routers that generated when an algorithm is run on the link state database. So each router's routing table is unique and contains information on how and where to send packets to other routers. So the routing table contains destination routes and how you can get into those. Now, the router builds this topology table using results of calculation based on the shortest path first algorithm. So the SPF algorithm is based on the cumulative cost to reach the destination. So the SPF algorithm creates an SPF tree by replacing each router at the root of the tree and calculating the shortest path to each node. So the SPF tree is then used to calculate the best route. So OSPF therefore places the best route into the forwarding database, which is like our routing table that we talked about earlier, which is used to make the routing table information. Okay, so the SPF is basically the algorithm that is used. Algorithm simply means it's just a step-by-step line of instructions on how to solve a problem. So in this case, you have so many routes in order to get to a destination, but so you need an algorithm in order to help you to be able to narrow it down to the one with the shortest path. So how does the link state, the OSPF carries out this operation? How does it do that? So to maintain routing information, the OSPF routers complete a generic link state routing process to reach a state of convergence. So the following are basically some of the link state routing steps that are completed by a router. The first one is to establish neighbor agencies. The second one is to exchange link state advertisement. The third one is to build the link state database. The fourth one is to execute the shortest path algorithm. And the fifth one is to choose the best route. Like I said, these are different operations that are covered by link state. So neighbor adjacency has to do with the routers that are directly connected to it. Link state advertisement has to do with advertisement of the link state. And then the database and SPF, as well as the best route, all combine to give you the operations of the link state. So to make OSPF more efficient and stable, OSPF supports a hierarchical routing using areas. Remember, we talked about the areas, area 0, area 1, the areas that you number. Now, an OSPF area is a group of routers that share the same link state information in their link state databases. So the OSPF can be implemented in one or two ways, either in a single area OSPF or a multi-area OSPF. So in a single area OSPF, you see that all the routers are in one area. Best practice is to use area 0. But in the multi-area OSPF, OSPF is implemented using the multiple areas in hierarchical fashion. So all areas must connect to the backbone area. Backbone area now in this case is now our area 0. So routers interconnecting the areas are referred to as area border routers. All right. But this module, we're going to focus on the single area OSPF version 2. The multi-area OSPF, like we said earlier, is hierarchical. And with the hierarchical, the backbone is this one here, area 0. So you see, area 0 has a connection to a different area, in this case, area 51. Area 0, in this case, also have a connection with area 1. So the advantages that it has is that it gives a smaller routing tables. So tables are smaller because there are fewer routing table entries, okay, because of the categorization or the grouping. So this is because network address can be summarized between areas, and then route summarization is not enabled by default, right? Another advantage is that designing a multi-area OSPF with smaller area minimizes the processes and memories that are required. Generally, link state protocols require large resources on each router, maybe RAM, processor, and stuff like that. So that's what is required. So another advantage, it gives reduced frequency of SPF calculations. You don't need to do the calculation all the time. So in multi-area OSPF, it localizes the impact of a topology change. When there is a topology change, maybe when a link goes down in this particular case, you see, when a link goes down, you see, it's limited within this particular area. The information is limited within this area, and then it just updates the area border router, which in this case is router 2. Okay, but in a single area, once there is a link goes down, the entire area is communicated. All right, so it reduces the frequency of calculation, and that localizes the impact of the topology change. Now, what about OSPF version 3? It is the OSPF version 2 equivalent, but this time around, it uses IP version 6 as a prefix. It uses IP version 6, or it supports IP version 6. And then the version 3 of OSPF exchange routing information to populate IP version 6 routing table with remote prefix. So you should note with the OSPF version 3 address families features, OSPF version 3 includes support for both IP version 4 and version 6. So the OSPF address families is beyond the scope of this curriculum. However, version 3 has the same functionality as version 2, but uses IP version 6 as the network layer transport communication with OSPF peers and in advertisement route. So OSPF has separate processes from its IP version 4 counterpart. So the processes and the operations are basically the same as in routing IP version 4 routing protocol. Okay. Now let's talk about OSPF packets, right? Let's talk about packets. The packets are we have the database description packets, we have the link state request packets, we have the link state update packets, and we have the link state acknowledgement packet. So I'm going to just play a video and then just to get some more explanation about these packets.
Hello everyone, let's jump into OSPF packets, and we get to talk about these link state packets that have a couple cool functions. To start off, we've got the type 1 packet, and this is known as the hello. The hello is used to establish and maintain adjacencies with other OSPF routers. Your OSPF router is going to say hello to another router on a link. This is used to discover those neighbors and build those adjacencies, which are being used with keep alives to keep track of the neighboring router. The next one is the type 2, and the type 2 is the DBD. That's the database description packet. This contains an abbreviated list of the sending router's link state database. It is used by the receiving router to check its link state database against the sender. These link state databases must be identical between both routers within the same OSPF area. Our type 3 packet is the link state request, known as an LSR. And this is used to request more information from another router about an entry in the database description message. The type 4 is the link state update. This is what we send as a response to the LSR. Someone sends you a link state request, you respond back with a link state update. You're announcing either new information or you're sending what was requested from the LSR that you received. Now, a link state update can contain several different types of link state advertisements known as LSAs. Type 5 is going to be the link state acknowledgement. The LSAC is actually able to acknowledge every other OSPF packet type except for a hello. You don't ACK a hello. And also we don't ACK an ACK. Those would be a forever acknowledgement going back and forth. So link state acknowledgements are awesome for acknowledging other packet types that aren't hellos and aren't acknowledgements. So let me jump into the OSPF link state updates, and first we're talking about those type 2s again. That type 2 database description packet, that thing is an abbreviated list of the sending router's link state database. And this is important because then we have that request, which is going to come up from another router saying, I saw your database and there's a specific item I need to know more about. And then we come to this, the link state update. That update is going to be in response to that request, or it's going to be an OSPF created message regarding a new network or something that's changed that's going on. Now, that link state update, as we mentioned, can contain many different types of link state advertisements. There's actually 11 different types of OSPF version 2 link state advertisements known as LSAs. I have them here on the right side. Now, these LSAs are the different message types that you might have a router receiving, which is part of an LSU. Now in CCNA here we really focus on 1 through 5, but we could go from 6 through 11, which is more of the advanced areas. So let's jump into an OSPF hello packet, and here we have it broken off into 2 sections. We've got the OSPF packet headers section itself and the OSPF hello packet section. Now, just a key reminder here, the hello packet is used to discover our OSPF neighbors and to literally maintain neighbor adjacencies. We've got a keep alive coming into play with this idea of a hello packet. Also, these hello packets include parameters that must be agreed upon in order for 2 OSPF routers to actually become neighbors. And lastly, when these hello packets are going back and forth between 2 OSPF routers, they're also used in the election of the DR, the designated router, and the BDR, the backup designated router. This is only on those multi-access networks using technology like Ethernet. Point-to-point does not use DRs and BDRs. So let's talk about some of these fields. Here inside of our OSPF packet header, we've got a couple different things that come into play, such as type. And the type at the top is going to inform our router if it's going to be a hello packet, a DBD, an LSR, an LSU, or even an LS acknowledgement. we've got the router ID field, and that is going to have a 32-bit value in dotted decimal notation. It'll uniquely identify the router that's created this hello message. We've got the area ID, which is about the OSPF area number from where the packet originated. We've got the network mask, which is that subnet mask associated with the sending interface for this packet. We've got the hello interval. That hello interval is going to literally specify the frequency in seconds at which the router sends hello packets. Now that default timer on multi-access is 10 seconds. We're going to have the router priority. This is used in the DR-BDR election that we mentioned. The default priority for all OSPF routers is 1. This can be manually changed though. This is values of 0 to 255. The higher, the better in becoming the designated router, which is the DR. We've got the dead interval, which comes back into play with timings, and this is the time in seconds that a router will wait to hear from a neighbor before it says, "You neighbor are dead and out of service." By default, the dead interval is 4 times the hello. If the hello is commonly 10 seconds, the dead is commonly 40. The designated router, that DR, this is the router ID, the label name of the DR. The BDR, this is the router ID, the label name of the BDR. And lastly, list of neighbors is just like it sounds. This identifies the router IDs of all adjacent OSPF routers.
All right, so thank you very much for that. So basically, the table below summarizes the 5 different types of link state packets that we use by the OSPF version 2 and the OSPF version 3. They have similar packets, okay? So we have the hello packet, we have the database description, the link state request, the link state update, the link state acknowledgement packets. So like what we have seen in the video, this is just a summary of it. Now, let's look at OSPF operation, okay? We're also going to listen to a short video that covers the different operations of OSPF, about the down states, the link initial state, the two-way state, the exstart state, the exchange state, the loading state, and the full state.
So we're here to discuss OSPF operational states, and the key focal point is on the progression that OSPF takes from beginning and activated on an interface to having multiple OSPF routers reaching convergence. And to complete this convergence, we have 7 states to go through. OSPF will transition from a down state to an init, from an init to a two-way, from two-way to xstart, from xstart to exchange, exchange to loading, and finally loading to full. We're going to walk through these states as we go through, so let's get started. When we first begin our discussion of OSPF in these operational states, we need to focus on OSPF activation. OSPF is going to be enabled on an interface. And when OSPF is enabled on an interface, your OSPF router must then determine if there's another OSPF neighbor on that same link. And to do it, we start in the down state. And then when we go to send a hello, we're going to start to initialize. And we say hello to a multicast target of 224.0.0.5. My router ID is 172.16.5.1. That's a 32-bit value from router R1. And it asks, is there anyone else on this link? Well, in order for us to stay in the initialized state or init, we need to get a response back. Because right now, we're going from OSPF has been activated, we're in a state of called down, to initialize by sending a hello. Now, when we get a hello back, we stay in the init state because we have seen someone else on this OSPF activated link. We've received a hello from R2. Also, R2 has added information into its message saying, I have a new neighbor. I have a neighbor known as R1. They have IP address 172.16.5.1, and they exist off of my interface gig01. When R2 sends its hello back, it's responding to us, and it's going to be sending it as a unicast targeting our router 1 IP address of 172.16.5.1. Now the neat thing is, since R1 has received a hello back from R2, and R1 sees itself in this neighbor list of R2, we're going to transition to the two-way state. R1 has received a hello from router 2, and in that hello it includes R2's neighbors, which also is R1. And since we see our own router ID in R2's neighbor list, we can transition to what's known as the two-way state. Now, with this two-way state, we want to talk here about an election that will occur, and this election is for a DR and BDR role-based routers. This election only occurs on multi-access networks such as using Ethernet. In this election, our routers will have a default priority of 1 on their links, and because the priorities are both defaulted at 1, it's a tie. So the tiebreaker goes to what's known as the highest router ID. In this case, R2 has 172.16.5.2 as its IP address, and that is its router ID it's taken. It has the higher router ID, so R2 will become the designated router. R1 has a lower router ID because it has a lower IP address. It is 5.1. That would be the backup designated router, known as the BDR. Our routers will then move onwards from the basics of that two-way state and the election, and they're going to go on to what's known as their synchronization process for their OSPF database. What we're focusing on here is synchronizing their link state databases, which is really their topology table. And to start this synchronization process, we use the XStart state. In the XStart state, this is the exchange start state. We have our routers choosing who's going to share their link state database first. Now, that link state database is known as the DBD packet, which is going to be a summarized form of their link state database. And in that exchange start state, the two routers pick out who goes first, and then the router that says, all right, I have the highest, so I will send my database description packet over to R1. Now, the cool thing is, it's a summary. It's a link state database, and the R1 router is going to acknowledge that it's received that summary. OSPF likes to be reliable. R1 then sends its own summary of its link state database, and R2 says, awesome, cool, I've got your summary as well, and responds with an acknowledgement. After we have viewed each other's summary, their database description packet, the routers will then respond back to each other with LSRs and LSUs. An LSR is a link state request. We can ask for more information on specific network entries that we've seen in those DBD packets that we didn't know anything about. The other router that receives your request would then respond accordingly with an LSU, which is a link state update, saying here's the info you needed. And again, OSPF likes to be reliable, so we have the acknowledgement coming into play. Now, the cool thing is, after all those LSRs and LSUs, you've reached full convergence. So let's take a step back. When we have this DR and BDR relationship coming into play in that two-way state, why is it there? Why is it important? Well, what we have are multi-access networks. And multi-access networks are commonly when we have Ethernet connectivity in between our routers. And in this case here, we have 4 routers with a switch interconnecting them. So what's the big deal? Well, this is going to create multiple adjacencies. What we have here is every router has an adjacency with every other router. What that really means is every router is making sure it has a full converged state between itself and the other 3 routers. This is insane as it gets into larger and larger topologies with more and more routers. Because with every extra adjacency, we now have excessive link state advertisements, which are messages in between our routers. Also, if there's any change in our network, we're going to have extensive flooding. So let me show you. So router R2 here has a change, and it sends out its link state advertisements notifying all of its other adjacent routers, which is all other 4 routers. Now those routers do their job, and they also notify all of their adjacencies that they've made with other OSPF routers. Now check it out here. OSPF is doing its job. It's doing it correctly. But look at all the excessive LSAs where each router is notifying every other router. What if we could do it better? Well, we can. By having a DR and a BDR elected inside of a multi-access network, we can have our router 1, router 4, and router 5 literally have a full state only with the DR and BDR. And router 1, router 4, router 5 will only have a two-way state with each other. They won't concern themselves with having the exact same topology table as each other router. So let's see what happens. So R1 has a change. R1 only notifies the DER and the BDR, saying, I have full convergence with you, here's the change. From there, the DR accepts that change, and then it notifies all of its routers that it has a full state with, which is everybody. But routers 4 and 5, they don't notify each other because they only...
So basically, that is the operations of the link state. Down state, initial state, and the two-way states as we have looked at. Now, the last thing I want us to look at today is the case of DR, BDR, brother, and drother. Okay, and an increase in the number of routers in a multi-access network also increase the number of link state advertisements, exchanges between the routes. So this flooding of LSAs significantly impacts the operation of OSPF. Now, interestingly, if every router in a multi-access network had to flood and acknowledge all received LSAs to all other routers on the same multi-access network, the network traffic would become quite chaotic. So on a multi-access network, OSPF therefore elects a DR, which is a designated router, like a rep, okay, like somebody that represents some others, to be a collection and distribution point for link state advertisements and received. Okay, so all the advertisements would, the DR will now be responsible for receiving it and sending it. So a backup designated router also elected in case the DR fails. So all other routers become druthers or DR others. All right, but we call it druthers. All right, a druther or a DR other is a router that is neither a designated router nor a backup designated router. But we should note the DR is only used for this dissemination of LSAs. That is it. So the router will use the best next hop router indicated in the routing table for forwarding of packets. This is where we'll draw the line for today's class. Thank you very much. Don't forget to subscribe to this channel for more videos. Thank you.